Let's explore world models in reinforcement learning and how to implement them for Atari Pong. World models are neural networks that learn to simulate game environments, allowing agents to plan actions in their imagination. Let's understand what world models are and why they're powerful. A world model is a learned representation of how an environment works, predicting future states based on actions. Given the current state and an action, the world model predicts what the next state will be. Mathematically, the next state equals a function of the current state and action. This allows agents to learn through imagination rather than costly real-world trial and error. World models typically consist of three key components. The three components are a VAE for vision encoding, an RNN for memory and prediction, and a controller for action selection. The vision component uses a variational autoencoder to compress high-dimensional game frames into compact latent representations. The memory component uses a recurrent neural network to predict future states and rewards in the latent space. The controller is a simple neural network that decides which action to take based on the compressed state. Let's see how to train the vision component that compresses Pong frames. The VAE learns to compress game frames into a small latent vector Z, then reconstruct the original frame from it. The VAE loss combines reconstruction error to preserve details, plus KL divergence to keep the latent space well structured. First, collect around 10,000 frames by playing Pong with random actions to get diverse training data. Train the VAE to compress each 210 by 160 pixel frame into a compact 32-dimensional latent vector. Next, we train the memory component that predicts future states. The RNN learns to predict the next latent state Z given the current latent state and action taken. The RNN takes the current latent state, action, and hidden state, then outputs the predicted next state and reward. We use an MDN-RNN, which combines a mixture density network with an LSTM to model uncertainty in predictions. Train this component on sequences of encoded states and actions from actual gameplay. Finally, we train the controller that decides which actions to take. The controller is a simple linear model that maps the current state directly to action probabilities. Instead of gradient descent, we use the CMAES evolutionary strategy to optimize controller parameters. The amazing part: we can train the controller entirely inside the learned world model, never touching the real game. Training in the simulated world is orders of magnitude faster than trial and error in the actual game environment. Let's outline the concrete implementation steps for Atari Pong. The implementation follows 4 clear steps: collect data, train the VAE, train the RNN, then train the controller. Step 1. Generate 10,000 random game episodes in the Pong environment using OpenAI Gym. Step 2. Train a convolutional VAE with 32 latent dimensions on these frames. Step 3. Encode all frames using the trained VAE, then train an MDN-RNN with LSTM on action sequences. Step 4. Use CMAES to evolve a linear controller that performs well in the simulated world model. Here's how the code components fit together. Organize your code into separate modules: v.py for the vision component, rnn.py for memory, controller.py for actions, and train.py to coordinate everything. The VAE uses convolutional layers for encoding and decoding with a bottleneck latent representation. The RNN combines LSTM cells with a mixture density network to handle stochastic predictions. World models provide several key advantages over model-free RL. World models excel in sample efficiency, training speed, transfer learning, and enable planning through imagination. Once the world model is trained, you can simulate millions of steps in seconds rather than hours of real gameplay. This dramatically reduces the number of real environment interactions needed to learn good policies. You can visualize what the agent imagines will happen, making the learning process interpretable and debuggable. However, world models also face important challenges. Key challenges include model errors, training complexity, and compounding errors over long horizons. The world model might not perfectly capture all environment dynamics, leading to sim-to-real gaps. Small prediction errors accumulate when planning many steps ahead, making long-term predictions unreliable. Getting world models to work well requires careful tuning of architecture and training hyperparameters. Let's summarize what we learned about world models for Pong. World models are learned simulators that predict how environments evolve given actions. They consist of three components: a VAE for vision, an RNN for temporal dynamics, and a controller for action selection. Train each component sequentially, first the VAE, then the RNN, finally the controller and simulation. This approach enables fast, sample-efficient learning by training agents in their imagination rather than reality. World models are a powerful technique for mastering complex environments, like Atari games with limited real-world experience.